Okay, here's video number 2 on gravitational potential. And we've we've talked about gravitational potential on the surface of the Earth. We say it's mgh, but that doesn't work when the gravitational force is not always mg, right? When little g is changing as you go further away from the Earth. So when you're talking about serious altitude or escape velocity or planets, things that are much bigger distances than just a ball, in your hand or in a room on Earth, something small, um, a baseball, right? We're talking about bigger distances. We have to use a different equation for gravitational potential energy, and I'm going to show you where this comes from, but this is the equation for gravitational potential energy. And this is looks different than what we've used, right? Okay, so the force of gravity decreases as you get farther away from Earth. So if you get to an infinitely far distance, you're going to have zero force, but until then, you still have some kind of force from gravity. And in order to lift something up, say you want to lift something up away from Earth, it's going to take force the whole way until you get to infinity. And this is a 1 over r squared graph, because it's gmm over r squared. And the work that it takes to lift something up is the integral of this curve. So that's a little bit of calculus. Let's take the integral of this function with respect to r. And we're going to integrate it from some initial r to some final r. And this is the work done. This is actually work done to go from farther away to closer. This is a constant. It comes out. Take the integral of this 1 over r squared and you get a 1 over r, or negative 1 over r. That would be a yeah, 1 over r, and then evaluate that. That's what this line is. Evaluate that from r initial to r final, and then you get this. Now, if you set the initial, if you move this r initial out to infinity, then you get this. And we like to set the initial r to infinity. We like to set the zero gravitational potential energy to infinity, and that's because the force of gravity is zero at infinity, so it just makes this easier. And so by always making the initial r infinity, or choosing our location of zero potential energy, remember we can always choose that, it's relative, to be at r equals infinity, then every other location is relative to there, and you just have this now one term, which is negative gmm over r. One thing to notice about this equation is that, well, it's negative. And what's going on here? If you think about pulling an object further and further away, say you have your Earth here and the object is getting pulled further away, that always takes more work. Even if it's a little more work, right? Tiny little area here. It's going to be more and more work until finally, when you get to that furthest point where r equals infinity, that's your maximum work done. That's your maximum value of UG, not your minimum, even though it's zero, right? We know the gravitational potential energy at r equals infinity is zero, but that's your max. And so everything else is negative. It's less than that. And that's an interesting effect here. We've always thought of gravitational potential energy increasing as you go further away from the Earth. It's still increasing, and it's increasing up until that maximum value of zero. So now that we've seen this strange equation, let's see how it's really useful. Here's the question. An object is dropped from 1,000 kilometers above the surface of the Earth. What will its speed be when it reaches the surface? Okay, so initial energy equals final energy. The initial is when it's 1,000 kilometers away, and that's only gravitational potential because it's not moving. And the final is when it's at the surface of the Earth. Now that is not zero anymore because everything now is measured relative to r equals infinity, right? So that's where zero would be, but this is not r equals infinity. This is at the surface of the Earth. So this is another gravitational potential energy term. So now we have this equation and we solve for V. Here's the solution using the constant for big G, the mass of the Earth, the radius of the Earth, and then this initial radius is the radius of the Earth plus the altitude, 1,000 kilometers. And you can see that when you solve for the velocity, you get 4,122 meters per second. If you solve this the old-fashioned way with a constant value of gravitational field strength, you would get the wrong answer. It would be too large. So that's why we have to use this gravitational potential energy now. Here's another example. This object is launched from the surface of the Earth with an initial speed, and how high will it go before falling back to Earth? Okay, again, we solve this using energy with kinetic energy at the launch, but it also has gravitational potential energy at the launch, and then it has the final gravitational potential energy at the higher radius. So we're solving for that altitude, and if you find the final radius and then subtract the radius of the Earth, you get 493 kilometers. Okay, a final example, and this is a really useful use for this equation. So you'll see you can calculate the escape velocity, which we couldn't do before. So we want the escape velocity for an object launched from the Earth. At what speed will the object not return to Earth? So what changes in this equation is we want the final radius to be infinity, right? So actually we want it to have zero gravitational potential energy at the final location and zero kinetic energy. So there's the equation for this one. Solve for the velocity, and that's the escape velocity. And you get 11.2 kilometers per second. So that's what it takes to launch a rocket from Earth and have it never return. Okay, there are your examples of gravitational potential energy.